Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Archana Aravindan with us today. Hello, Archana.
Hello,
Hi
thank you so
there.
much for having me. It's great to be here.
Well, it's nice to meet you on the top of a mountain with a couple of telescopes on it. So I think that's pretty awesome. Very cool.
Yeah, these are some of the greatest telescopes available here on Earth, and a lot of my PhD is possible because of these telescopes. So shout out to Keck telescopes on Mauna Kea. So that's what these are.
Yep, and I'll come back to that. And um, but what is your real geolocation? What,
Uh,
where
so
are you?
I'm a PhD student at Riverside, California. So this
Riverside.
is yeah, we are a little bit east of LA, I guess, if that's easier for people to locate, but pretty much in the desert. So that's where I'm at.
And on this November 25th of 2024, as we record this, I'm in Phoenix and I'm definitely in the desert. And we're definitely entering our winter mode. A little cooler in the
Yep.
morning, warms up in the afternoon. It's very pleasant. Side's probably comparable. So
Yep.
very cool. And Archana, when do you graduate?
Hopefully soon. So this is my fifth year. I'm hoping to graduate sometime between next year or the year after, depending on how things go. Yeah,
Cool.
we'll see.
Very cool. Well, let me be the first then to congratulate you, Dr. Aravindan.
Thank you in a way in advance, but thank you.
It'll be here soon enough.
Yeah.
Very cool. And Archana, what do you like to do for research?
So I'm an observer and I like looking at black holes or what do black holes do in small galaxies. So I basically study AGN outflows in dwarf galaxies. And I try to do that observationally by looking through these telescopes
Mhm.
mostly. So that's what I do.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A closer look at dwarf galaxies exhibiting mid-infrared variability, active galactic nuclei conformation, and comparison with non-variable dwarf galaxies. And Archana, take us away.
Yeah, thank you so much, Frank, for reading out the very long title. I started off my PhD with AGN outflows, and then as I was doing these AGN outflows, I realized that it's actually kind of hard to find these AGN in the first place in dwarf galaxies.
Yeah.
So to
Yeah.
find outflows, you need to find the AGNs in the first place. So that's kind of the motivation for this project. How do
Cool.
we come up with better ways to really find these AGN in dwarf galaxies? So that is what this paper is about.
Cool.
And of course, this work, before starting off, I would like to give a big shout out to my amazing co-authors. So my wonderful advisor, Gabby Canadizo. She's just amazing and she's been just so supportive in all throughout my PhD. So very grateful to have her as my advisor. And of course, my wonderful collaborators from the East Coast, Nathan and Shabita, who are experts on mid-infrared variability. And they also taught me a lot about using this particular technique to find AGNs in dwarf galaxies.
Good.
And Thomas Vaughan was previously in my group. He's currently a postdoc at Hiroshima University, and he taught me everything about working with NIRIS on Keck. So if people in the audience have ever worked with NIRIS, it's a wonderful instrument, gives amazing science, but it can be challenging to work with. And Thomas really developed a lot of the analysis and reduction packages to work with NIRIS, and
Very
he's
cool.
passed on all that knowledge to me. So I'm very grateful to him.
That was a great
Yeah.
shout. Great shout out.
Yeah.
Good.
All
Okay.
right.
Let's go.
Right. So, really zooming out and giving a very big picture is why do we care about black holes in dwarf galaxies? So, right now we know that every massive galaxy in the universe has a black hole at its center, and this black hole plays an important role in regulating a lot of galaxy properties. But we really don't know how do these black holes get there in the middle of these galaxies? How do they reach their massive sizes? In short, we don't really know a lot about these black hole seeds, like how did they form? How were they when these black holes were babies?
Okay.
So to do that, we might need to go back to the early universe, and that might be hard to do at times. So that's why we look at things in the local universe, which are dwarf galaxies. So
Okay.
dwarf galaxies are your smaller galaxies, but they are expected to be very similar to the galaxies of the early universe, because it is typically expected that galaxies started out small and then they merged and ended up as the big galaxies we see today. So
Okay.
dwarf galaxies are more likely to be similar to the galaxies of the early universe. And any black holes that are present in them are more likely to be similar to the early black holes of the universe.
Mhm.
So that
Yep.
is what we're going off.
Cool.
And then studying these black holes are important because they give you clues about what could have been the early black holes in the universe. So
Right.
there are two kinds of like popular theories. So the one popular theory for the formation of the first black holes is that uh, they were formed from the collapse of really massive stars. And the
Okay.
second one is that they were formed from, direct collapse of gas. So there are subtle
Okay.
differences between the properties of the black holes that are formed in these two ways. So if you have the one that's formed by the collapse of stars, they're more likely to be less massive, so about 100 to 1,000 solar masses. If they were formed by the collapse of gas, they're more likely to be more massive.
Mm-hmm.
Uh,
Mm-hmm.
yeah, exactly. Uh,
Mm-hmm.
so when we look at these black holes in dwarf galaxies and we are able to estimate their masses, that would give us an idea of what were the masses of the black holes in the early universe, and by extension, we can predict how were these first black holes formed. So that is the really big picture of why we want to study, or we want to find black holes in dwarf galaxies.
Well said.
Uh,
Very good. Okay.
Yeah, so this is still a very recent development. So I guess we are only now very recently trying to understand or finding out that even dwarf galaxies can host black holes. And that's thanks to all these amazing large surveys and the telescopes technology that's bringing about this transformational change. And of course, JWST is also doing a really good job of doing the same thing in the high universe. So it allows us to study both in, high redshift universe, and it allows us to study both kind of in parallel. So
Yeah.
this is an exciting time to be doing this.
Indeed.
Um, right. So I think if you could scroll down a little bit,
Sure.
we you can yeah. So I guess one of the major challenges in detecting black holes. So when we look at black holes in dwarf galaxies, we look at active black holes, or AGN. Because these are the bright ones, which can be easily spotted as compared to like a black hole that's just sitting there. It's hard to spot that
Hard to see that.
all the way from here on Earth. So we look especially for AGN, but even looking for AGNs is challenging in dwarf galaxies. When you look for AGNs in more massive galaxies, these are really massive black holes. So they have really massive signatures associated with it. So it's pretty easy to spot them. They are the bright centers of galaxies, which is why the names came out, active galactic nuclei. But when we look for AGN and dwarf galaxies, people soon realize that it is challenging because these black holes are smaller, less energetic than black holes in more massive galaxies. So they're
Yeah.
not going to give off any obvious signatures, that makes it easy to spot them.
Big, massive.
Uh, yeah, exactly. Yes. So we don't have the massive jets, and even the more commonly used diagnostic diagrams, like the BPT diagram, for example,
Mm-hmm.
which separates AGN and star forming regions based on what causes the ionization of emission lines, for example.
Got
Uh, yeah. So a lot of people have found out that this also does not do a good job in finding AGNs in dwarf galaxies. So, if you are familiar with the BPT diagram, it makes use of lines such as oxygen and nitrogen.
it. Yes.
And these are what astronomers call metals. So, anything other than hydrogen, um, these are called metals. And it's kind of hard to produce these metals in dwarf galaxies, which are smaller.
Mm.
So, it's kind of hard to get those ionized lines, which contribute to the BPT diagram in the first place. And also in dwarfs, you can have very similar signatures. So the stars and the black hole can be equally comparative in energy. So
Yeah,
you
yeah,
might sometimes actually have a black hole, but
yeah.
the stars might be overpowering. So you might see the star forming region, ionization, and then your galaxy is still in the star forming region of the BPT diagram, but it might be actually hosting an AGN, but it's just hidden.
Right, right.
Uh,
Mm-hmm.
yeah.
Okay.
So
Um,
a lot of challenges with traditional diagnostic diagrams, which is again great motivation for finding better ways to find AGNs in dwarf galaxies.
okay.
And one promising method is variability. So AGNs are known to be variable, so you can see their flux change with time. So
Yes.
variable across all kinds of wavelength ranges. That's what AGN special. And this is typically attributed to the fluctuations in the accretion disk that is surrounding the central black hole. So that is what contributes to the brightness of these AGNs and also contributes to their variability. So this is, again, well known, well studied in more massive AGNs, and naturally people try to extend it to lower mass AGNs and try to see if maybe this is a better way to find out all these hidden AGNs in dwarf galaxies.
Okay.
So initially, this was done with the optical variability with some success, and then mid-infrared variability. So this is now variability in the mid-infrared wavelength regime.
Okay.
Has also been popularly explored. There are some advantages of using mid-infrared variability over optical, and one of these is because, so mid-infrared variability is essentially you have the variability fluctuations from the accretion disk, which gets reprocessed by the dust in the surrounding the accretion disk, and that is what is manifested as mid-infrared variability. So sometimes it's easier to spot these because mid-infrared is less affected by dust. For example, if you have optical variability from the disk, that gets absorbed by the dust sometimes, and it's hard to see it as optical variability, but it might be easier to spot as mid-infrared variability.
Okay.
So that is one motivation. And you also have less chances of contamination. So you can also have other things that contribute to variability, like supernovae, for example, which are also variable. And then this work that shows that the mid-infrared variability is, you are less likely to get confused between like a supernova as compared to an actual AGN. So
Okay.
that is why mid-infrared variability is sometimes considered a better way. And that is something we try to see, is it truly a good method to find missing AGNs?
Cool.
Yeah, so that is so that kind of brings me to what we were trying to do in this paper. So we specifically look at mid-infrared variability. So we identify a sample of galaxies which are variable in the mid-infrared using WISE surveys to generate light curves. And then we try to see if something is variable in the mid-infrared, how likely is it that it is actually an AGN that is contributing to the variability, as opposed to like any other infrared transient that could also be contributing to variability. And this gives us a sense of, if something is variable in the mid-infrared, how confidently can we say that this is actually because of an AGN? And then we use that to actually find missing AGNs or hidden AGNs in dwarf galaxies.
There we go. Might be plain sight. Very cool. Very cool. I'm with you.
Yeah, so that is the introduction, I guess, quite a long introduction, but that is the motivation for this paper. So we start off.
Perfect.
Yes, so we start off again first by selecting our sample. So first we look, because this is on mid-infrared variability, we initially look for objects that are variable in the mid-infrared. So again, this is really good work done by Nathan, actually. They did a analysis in one of their previous papers to look for mid-infrared variability, and we kind of extended that for this with the latest release of the WISE survey. So again, we matched a couple of catalogs, and then of course we made use of the WISE catalog to get these light curves. So it's possible to do that with WISE because WISE kind of sees the same target again in like 6 months. So that is like the cadence of WISE. So we have around, I think it is around 10.4 years worth of photometry. So this is like
nice.
So around 20 circles. So you're able to see variability across a decent amount of time. So that is what we try to do. So we do that, and then we get these light curves. So that is what we show in figure 1.
Figure 1. Take a look at a WISE light curve here. There we go.
Yeah, so now so there's a very gentle variability that you can see. Again, it kind of goes to show that how difficult it is to actually look for variability in these objects. So there's variability in the WISE 1 colors, which is 3.4 micrometers. And then WISE 2 as well, which is 4.6 micrometers. And then we also get the color, W1 minus W2, to see that variability a little better. And then, so yeah, this is how we generated a light curve. So we used a combination of statistics as well as visual inspection because sometimes you might have like a variable light curve which passes statistic test, but it's actually being like a supernova. So supernova variability is very evident, like it's like a flare and then it comes down. So it's very
Right.
evident that it is a supernova.
Okay.
AGN variability is more gradual. So you don't see a sudden rise and a dip. So that is what we were essentially looking for. So we did all those tests, and then we ended up with 25 targets, which we think have good indicators of AGN-like variability in the mid-infrared, and
Huh.
that was our parent sample.
Okay. Very cool. I am with you. Okay.
Yeah.
Mm-hmm.
So now we have our mid-infrared variable galaxies. So now how many of these actually do have an AGN? So we try to do that by
Right.
just by trying to see if there are any other indicators of AGN activity in these galaxies by looking at a bunch of optical uh, diagnostics as well as infrared diagnostics. So we just looked through literature and tried to see how many of these have already been identified as AGNs. And turns out a good sample of them were identified as AGNs. So around 12 of the 25 did have a combination of optical techniques. So some of them
Okay.
had broad lines, some of them had they were also BPT AGN. Some of them had helium-2 emission. So these are all very commonly used AGN indicators in the optical. And then a good number of them did satisfy that criteria. So this goes to show that mid-infrared variability, in fact, is already doing a good job of picking out AGNs. So it's accurately
Good.
tracing AGNs in dwarf galaxies. So we are good there. But we still had half the sample left, which should not have any obvious signatures of AGN. So what we wanted to do with these is to look at the infrared spectrum to see if there are indicators of AGN activity in the infrared, because like clearly none of these were marked as AGN in the optical. And again,
Uh-huh.
the optical can miss a lot of AGNs. So we were trying to see again if the infrared can do a better job of finding AGNs in these
Cool.
dwarf galaxies. So we did follow-up spectroscopy using NIRIS on Keck. And this table essentially sums up the entire results. So these are all our targets, and then how they would, what indicates that they are in AGN,
Mm-hmm.
other than mid-infrared variability. So everything with a tick mark has been identified in literature. Everything with a cross has been identified in this work.
Right.
Um, so yeah, a combination of both helps us identify AGN in these or confirm AGN in these
Yeah,
dwarf
both.
galaxies.
Yeah, yeah. Okay. Very nice. Nice sample.
Yeah,
Okay.
right. Yeah, so that's what we do. We use NIRIS on Keck, do spectroscopy for how many of our targets we do it, but then with astronomy or especially observation astronomy, weather plays a big role. So,
Yes, it does.
so we weren't able to see our entire sample, but we did get a good number of observations with near-infrared spectroscopy, which is what we elaborate our observations. And all the observational details of our observing nights and observing runs and how we reduce the data has all been listed out very nicely in this particular section.
Yep, that's
Um,
concise paragraph. Resolution 3400. Okay, good. Hmm.
yeah, and then if we just go up to figure 2, I believe.
Sure. Let's go up to figure two and we're going to look at BPTs and
Yeah,
VO.
so these are the commonly used BPT diagrams for all the targets. And then here you can kind of see, so everything in dark blue was uh, targets which were not confirmed to have an AGN.
Okay.
In literature, and then that were actually observed with NIRIS. And then you can see a lot of them, even overall, do not have very strong indicators of AGN activity from the BPT diagram. So a lot of them are star forming on the BPT diagram. So that makes it again kind of goes to show you that how challenging it is to use traditional
Right.
diagnostics,
Yeah.
yeah, like the BPT diagram to actually
Yeah,
look for AGNs.
yeah. Especially when there's gradients across it.
Yes.
Yes.
Yeah.
That's
Yeah.
a challenge.
So
Hmm.
yeah,
Okay.
so this is, I guess, this kind of shows you that yes, it is challenging to like just rely on indicators like the BPT diagram, for example, and we really need to look for other methods to find AGNs in these galaxies.
Okay. Good. Good. Okay. So if this was all you were relying on, that would be tough. Okay.
Yes.
Okay. I'm with you.
Yeah.
Hmm.
Okay, so then moving on, I think section three is where we talk about our analysis or what we found out from our NIDIS observations. And then this was specifically to look for AGN activity. And one of the things we found was a kernel line in one of the targets, J1205.
Interesting.
So kernel lines are lines of very high ionization potential.
Uh-huh.
So they are
Couple.
like formed from really highly excitational collisional. So these are things like silicon 6, sulfur
Yeah.
9. So a
Yeah.
sulfur atom that has, has, it's like sulfur 9. So a lot
Yeah,
of,
there you go. Couple nine.
yeah, yeah. So your electron is, jumped up from a really low energy shell. So you need to have a lot of energy to actually allow the electron to knock out.
Yeah.
And this is expected to be possible only by a really energetic activity, which is something like a black hole, is is what can cause these excitations. So whenever you find kernel lines in your spectrum, it's typically attributed to AGN activity as opposed to, like star formation or
Yeah.
like supernova. It's less likely that that a star forming activity contributed to these lines. So it's generally accepted that if you have a kernel line, it's caused by an AGN. So it's like a telltale sign of AGN
Yes.
activity in galaxies.
Nice.
So
Okay.
this is good for us. So we have a target that's variable in the mid-infrared, and it has a kernel line showing that it does have very likely has an AGN in this target.
Okay.
And the really nice thing about this target, sorry.
Yes. Yes. Go ahead. Go ahead.
Yeah, the really nice thing about this target is that it has a really low mass. So I think if it looks down, it has a stellar mass of 7.5 solar masses,
Okay.
and then a really low metallicity as well. So again, it has only a metallicity of 7.46, which is subsolar.
All right.
So even in targets which have very low stellar masses and low metallicities, it is possible to use mid-infrared variability to find AGN activity. So this was very interesting. Thing we found. So if you scroll down to figure, I believe 3 or 4.
Okay. Let's slide down. Three is the
Yeah,
NR
figure
spectrum.
3.
Go down to four.
Yeah,
Okay.
yeah. No, figure 3 is fine.
Oh, figure two's fine. Okay.
Yeah, so this is the kernel line, sulfur 9 that we found. So this is, again, a really telltale sign of AGN activity in this galaxy. So this is what we detected, which is very exciting. So it's possible to even find AGN in really low mass, low metallicity galaxies using mid-infrared variability.
Bang. And bang. Iron two.
Yeah,
Yeah.
so iron 2 is a more commonly found line. It's not a
Sure.
kernel line, but sulfur 9 is the kernel line that we found. Uh, yeah, in
Okay.
this particular galaxy. So that was exciting.
What is the blue line here centering or marking?
So yeah, so that is the kernel line. So this is the entire range of spectrum, and then
Okay.
we just zoom in
Got
to
it.
show a better fit.
Got it.
So yeah,
Yes, I'm with you. Okay. All right. Okay. What happens at longer wavelengths?
yeah. So this is
It's kind
again
of
an
crazy.
issue with infrared spectroscopy. You have telluric absorption. So we have
Okay.
water in our
Uh,
atmosphere, which kind of absorbs has a lot of transitions in the infrared. So that really manifests in your infrared spectrum, especially from the
got it.
ground. So you
Yeah.
have all these absorption lines. So that is a region of telluric absorption. So we
Okay.
typically, yeah, we would have to like omit those lines, missing out a lot of information, which
Yep.
is why space-based infrared telescopes are great. You don't have to deal with any of these absorptions. So that was really nice to see some of the initial GWST spectra. And I
Uh,
was like, where are the absorption lines? And yeah, they're just not there. And you get a nice clean spectra in the infrared, which is exciting.
Very
Yeah.
cool. Very cool. Okay. Thanks. Okay. Three. So we got a spectrum. Is it do. Okay. Now we're at spectrum. Okay.
Yeah. So again, sulfur 9 was very obvious. There was a hint of a silicon 6, which is what we show in figure 4. So silicon 6 is one of the more commonly found lines. So that's in figure 4. Um,
Mhm.
and then we don't really find like it at a confidence level that is expected to like report it as a
Okay.
this thing
Ooh.
as a line for sure, but we do see a hint. But again, if we were able to have all the time in the world to observe the telescopes, better signal to noise, and it might pop up. But
Yeah.
again, based on what we had, we do find just a small bump, but it's possible that there's other kernel lines in this particular target as well.
Yeah.
So,
Fair enough.
uh,
But
yeah,
maybe. Okay. Good. Okay. And
yeah. And then we do like talk about again, so kernel lines is a difficult thing to find in general in a lot of galaxies. So when you find a kernel line, it's like for sure that it is an AGN.
yeah.
But when you don't fire kernel line, it doesn't necessarily mean that there is no AGN.
Yes.
It's just one of the things which are very hard to detect.
All right.
So you need like really good signal to noise spectra. So we just kind of try to show here that our we do have upper limits on the rest of our targets, and they all kind of fall in the range where it could have been detected with better signal to noise.
Yeah.
So yeah, nothing really rules out the possibility that these targets don't have a kernel line or don't have an AGN in most of the targets. We were just like limited by time and
Sure.
noise in the data.
Okay. Okay. Tantalizing hints, we'll call them.
Yes.
Okay.
Yeah, so that was the exciting discovery of sulfur 9. So again, J1205 is very popularly studied in literature. It's also been known as a green pea galaxy. So these are galaxies with very high O3 ionization lines, which are found across the universe. And then there's also evidence of AGN activity in them based on Weiss colors and also mid-infrared variability, but this is the first time we found like a kernel line in this particular target. So that again adds up more evidence that this little green pea galaxy is likely hosting an AGN. So that's a very exciting
Very
thing
cool.
for,
That's very awesome. That'll make for
yeah.
a very lovely thesis chapter.
Yes. Yeah, and then we also have other evidence of AGNs in the rest of the targets, and some of these are broad passion alpha lines that we detect.
Yep.
Again, broadening of the hydrogen lines is also a very good indicator of AGN activity. And then
Okay.
we find two of these broadline components we find broadline components in two of the targets, and you can see them, I think, in figure 6. Yeah,
Interesting.
and that's the interesting part that
Yeah,
these
yeah,
had
yeah.
broad
Big.
lines in the near infrared and not in the optical. So in the optical, you have your lines such as H alpha, H beta, and then the SDSS spectrum does not show any obvious signatures of broadening in the optical lines for these targets, but then
Okay.
they show it in the infrared. So again, this kind of shows that the infrared is maybe able to probe the AGN activity a little better. It's possible that the AGN activities in the optical are kind of
Yeah.
getting hidden in some way because of dust or other factors.
Other
But
things. Very cool.
yeah, yeah.
Okay.
So we have this broad line, which is indicated by the pink, magenta-ish line, which is
Uh-huh.
in these targets, so
Mm-hmm.
showing the presence of a broad line in them. Um,
Each one there. Okay, good.
mhm.
Uh-huh. Okay. Boo, boo, boo. Okay, cool. I'm good. I'm with you.
Yeah, and then we're also able to derive a black hole mass. So there are empirical relations in place, which is seen
Oh,
in equation 1 in this particular paper. So you can
that's why we're doing
use
that. Okay.
yeah, you can use like the width of these lines and the luminosity of the Paschen alpha to get a black hole mass. And then we've listed the black hole masses in table 3.
Okay.
Uh, yeah, those are the masses of the black holes that were formed. And then for better visualization, you can also go down to figure 7, where we plot our calculated black hole masses
Oh,
with
nice. Nice.
yeah expected values, and it kind of fits nicely, just slightly above the expected range of a black hole. If, if there was a black hole in these galaxies, what would have been the mass? So again,
Nice.
a little bit more evidence that it's likely hosting a
Mm-hmm.
black hole of that particular mass in
Mm-hmm.
this galaxy.
Very cool. Nice detection. Good. Okay.
And then one last thing we do with the NIRIS spectrum is make use of near-infrared diagnostic diagrams. So we have plenty of optical diagnostic diagrams like the BPT diagrams, which makes use of optical lines. And then now there was a dearth of near-infrared diagnostic diagrams, mostly because it was hard to do near-infrared astronomy. So we did not have a lot of galaxies with spectra in the near-infrared. So it
Uh-huh.
was hard to, have like a region where it's AGN, a region where it's star forming, like we have in the PPT diagram. But now we have plenty more infrared telescopes. KWST-41 is really spearheading a lot of galaxies with infrared spectra, and that allows us to make these near-infrared diagnostic diagrams. So they're
Yes.
very similar to optical diagrams, but now we make use of near-infrared lines.
Yep. Yep.
So we try to see where do these targets fall in one such diagnostic diagram. So if you go down to figure 8.
Drum roll. Okay. Figure 8. Very good. Rolling out. Summary figure 8 and NIR diagnostic diagrams. Okay.
Yeah, so this was done by Calabro et al. So they used a lot of modeling, a lot of actual data from database galaxies, as well as other infrared spectrum of galaxies with AGN and without AGN, to try to see where do these limits fall, like the limits of star formation and the limits of AGN, which will allow us to separate between the two. So we see where do these variable dwarfs fall on a diagram like this. And then one thing we find that is that if you remember our optical diagrams, a lot of these were very strongly star forming, or definitely closer to the star forming regions.
Right.
But then here we see all the variable targets, they actually move closer to the AGN region. A few of them actually are in the AGN region of this particular diagnostic diagram.
Yes.
Everything in blue are the variable targets. So you
Uh,
can see a couple of them do
uh,
actually cross the threshold and are likely to be AGNs. All of them do in general move closer to the AGN part, even though some of
yeah.
them are composite, they are closer to the AGN line as compared to the star forming line in the previous optical diagrams.
Right.
So this indicates that maybe near infrared diagnostic diagrams can do a better job of finding these AGNs as compared to optical
Mhm.
diagnostic diagrams. Um, this is just to show that maybe this is an important method, especially going forward in the future, to use to find AGNs in the universe.
Mm, okay. Okay. U is ionization. Okay. Got it. Got it. Uh-huh. That makes sense. Okay. Cool. I'm with you.
Yeah, so these are our results from the NIDIS, which is all summed up very nicely, I think, in the following figure. Now that you're there, you can just go down to the flow chart, figure 9. Um,
There we go.
yeah, so we started with 25 targets, and then half of them, or most half of them, were classified as optical AGN. We observed 9 in the near infrared. We could not observe 4 because of bad weather. But even in the 9 we find evidence of AGN in more than half of them. So there
Yeah.
was a kernel line, there were
Expect.
broad fashion alpha lines, there were diagnostic diagrams which help us identify AGN. Um, so by the end of this, we find that a significant fraction, almost 70% of the targets which are variable in the mid-infrared, have very strong indicators of hosting an AGN based on other methods. So this kind of shows that
Good.
mid-infrared variability can do a good job of finding AGNs
Nice.
accurately in dwarf galaxies.
Nice. Very good. Very good. Okay. Uh-huh. Yep.
Yeah, and then another thing we do is also try to compare it with non-variable galaxies. So again,
Okay.
is there something special about these variable galaxies, the host galaxies of these variable targets, that makes it easier to like find the variability essentially, especially when you're talking about diagnostics in the mid-infrared, they're kind of tricky because you also have a lot of contamination from star formation. So you want to make sure that anything that you are, detecting in the mid-infrared particularly, or the infrared in general, is actually you can say confidently that it's an AGN and not like a star forming interloper. So
Right.
we want to be very sure. So we try to see, is there any difference between the properties of these variable targets and other non-variable targets, to see if there's any difference in the host galaxy properties between the two. So we set up this comparison between our target sample, and then we selected a control sample of galaxies. So
Okay.
these were non-variable targets, so they were not variable essentially in the mid-infrared. but they had similar Weiss colors, so W1 minus W2, and
Okay.
also similar mass, so that we were doing an apples to apples comparison
Yeah.
to try to understand what's different between the two.
Okay. I'll bite. Okay. Mm-hmm.
Yeah. So we did not find any significant difference in a lot of like optical properties of the host galaxy. So if you go down to figure 11,
11. Okay. Doot, 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 doot. Okay, there's our W's and figure 11s of the variables and nons. Okay.
yeah. So these are this is a summary of the properties or the commonly observed optical properties. So we did not find any very telling differences between the two. They were similar in things like O3 luminosities, star formation rates,
Okay.
colors, and even maybe in extinction values. So
Right.
nothing very obvious that sets the variable galaxies apart from non-variable galaxies in terms of host galaxy properties. Uh, so it's again kind of shows to go tell you how hard it is to again find these targets. So you cannot just look
Yeah.
for certain group of galaxies and try to find variability in them. It
Yeah.
does seem pretty hard unless you are explicitly looking for variability.
Yeah.
Um,
Those are pretty close. So there's no signature other than variability.
yes.
Okay.
But we did find like some again interesting differences we'd like to comment on. Again, this kind of goes to show that mid-infrared variability is in fact accurately tracing AGNs. So one difference we find is in
Oh,
the metallicities between the two samples.
okay.
So if you scroll down to figure 12,
2012. And ooh, okay.
yeah. So again, we characterize metallicity by just the N2 over H alpha
Mhm.
values. So if you have higher values of N2 over H alpha, it indicates that it's higher metallicities.
Rich
Uh,
for
yeah, yes. And we find that overall, most of the variable targets do have higher metallicities as compared to non-variable. So you can see just two of the variable targets are, in the lower range of metallicities. So they have metallicities less than or the ratio
one
N2 over
list.
H alpha is less than -1.
Yeah, yeah.
Uh, yeah,
Okay.
and then you have a more significant number of variable targets or non-variable targets in that range. Um,
Okay.
so again, this could just be like an observational bias. Like it's easier to find, uh, you know, these AGNs in galaxies with higher metallicity. So maybe it's just it just goes to show that the AGN is contributing to the metallicity or increasing the metallicity in these galaxies. So it shows that maybe variable galaxies do have higher metallicities because they have the AGN in them, which is pushing it to higher metallicities.
Right, right. As a driver. Uh-huh. Cool. Well, we're going to come back to that. Very good. Okay.
Yeah, and then we also find that a larger sample of these variable galaxies also have broad H alpha. So they are so this is a plot of the O3 velocity, the width of the O3 line as compared to
Mm.
the H alpha, and then
Uh,
we find that there are some of these targets which have very obvious broad lines, and this was also how they were actually identified as AGN by other methods.
uh-huh.
Um, so this was kind of surprising. So when you have like a broad H alpha, this kind of shows you that it's a type 1 AGN as compared to a type 2. So when you have a type 1 AGN, you're looking at it like at an angle, which allows you to see the broadline region. So you're
Right.
not seeing through the dust, which is what you do when you see it as a type 2 AGN. And then we would typically expect that mid-infrared variability does not have this preferential bias towards finding, it's found more in type 1 AGNs
Okay.
because it doesn't really matter. Like mid-infrared variability should be the same whether you see it in the
Could be.
disk or
Yeah.
above.
Yeah. Yeah. Yeah.
But maybe this shows that it is actually, in fact, easier to get variability when you are actually looking at type 1 AGNs, which is what a lot of people have also found in literature that
Okay.
variability is more pronounced in type 1 AGNs as compared to type 2.
Yes.
It could also be that you have a completely different origin for variability. So there's
Yeah.
some works which suggest that variability comes from the polar regions as opposed to the dust surrounding the accretion disk. So when you
Okay.
have variability
Okay.
from the polar region, and then that kind of
Mhm.
explains why you get
Okay.
more type 1 AGNs with variability. So again, this raises interesting questions about the nature of variability itself, which is
Yeah.
what we
Yeah.
find that was exciting as well. And then
Cool.
finally, we also look at the Weiss colors, which is our
Oh, yeah.
figure 14.
Yeah.
And then if you recall, I said we selected the controls based on similar W1 minus W2 colors. So that's on the y-axis. You can see the histogram on the right, and you can see the colors are in fact very similar. But we find that the W2 minus W3 colors are in fact quite different for the non-variable
Okay.
targets as compared to the
Okay.
variable targets.
Okay.
So even though they have similar W1 minus W2, non-variable targets have higher W2 minus W3 as compared to the variable target. So that's the x-axis, and the difference can be seen on the histogram on the top.
Right. Okay.
Yeah, so you can see
Mm-hmm.
there's a,
Mm-hmm.
a significant difference. So this also kind of shows that so W2 minus W3 has been, it's caused more likely by starburst activities. So when you have a high W2 minus W3, this shows that there's a lot of starburst activities that's
Yeah. Yeah.
contributing to that. So this essentially kind of shows you that even though you have two targets with similar W1 minus W2, it's likely that AGN activity is what is causing the W1 minus W2 in variable targets, whereas for non-variable targets, it's possibly the starburst activity. So you kind of need both to see which one's
Right.
contributing to the AGN. But we
Uh-huh.
find that the variable targets, it's actually the AGN which is causing the reddening. Again, goes to show that there is a good chance that these variable targets are actually hosting an AGN as compared to an interloper.
Cool.
Uh, yeah, so this is all we found. And then we've listed them out, and then to our conclusion. So I think if you just look, yeah, so we find independent confirmation in about 68% to 70% of our targets. So half of them was done initially uh, by optical methods, and then the rest were confirmed using in this particular paper, using a combination
Mm-hmm.
of
Mm-hmm.
night spectroscopy and then also comparing it with different variable and non-variable galaxies. Uh, yeah, so this goes to show that mid-infrared variability can in fact do a good job of finding AGNs in dwarf galaxies. And it is a very cost-effective method. So you don't need, expensive spectroscopy. You don't need to spend a lot of telescope time trying to find, all these signatures of AGN. You can just
Okay.
have your mid-infrared variable target, and there's a good chance that it is actually accurately finding an AGN. So you can be sure that, at least reasonably sure that it is doing a good job of tracking AGNs
Very
in
cool.
dwarf galaxies.
Very cool. Very cool. Archana, I want to thank you so much for walking us through your very awesome article.
Yeah, thank
Uh,
you. Pleasure.
It was great. And you certainly picked my questioning there at the end. So I'm curious because you were hinting at it. Where do you think we go from here, given the published article? Is there going to be a time where instead of having 9 of these, we have 90 of them in the mid-infrared? Is there a time for that coming? Is there additional analysis that could be performed on the 9 that are known to maybe help pick up other signs of AGN activity or detection of AGN, I should just say. So where do you think we go from here? Next steps.
Yeah, I think it is very exciting, like just in general for like infrared astronomy. So again, JWST is doing a lot of great infrared science,
Mhm.
and especially because of all these detections of possible black holes in the early universe that's been found by JWST, and because it has all these infrared data, I think it's going to be definitely easier to look for variability as an indicator to find AGNs across the universe, from the early universe to the present universe. And
Cool.
this kind of shows that it is doing a good job. So maybe with all the, more data available, we can get, stronger estimates,
Mhm.
better ways of finding them. And of course, the good signal to noise, should make it easier to find them much more easily as compared to these ground-based techniques or ground-based telescopes. And also, there's a lot of transient astronomy coming up as well. There's a lot of telescopes just dedicated to transient astronomy.
Oh yeah.
Um,
Uh-huh. Yeah.
so that is also going to be interesting to use those telescopes to find, more of these variable targets and try to determine
Very
if they
cool.
actually do host an AGN. And of course, yeah, I think we are getting closer and closer to really finding out how the first black holes are.
Right.
And I think this would be a good way to really pin it down and hopefully pin it down and help us understand how did the black holes get here. Yeah.
Very cool. Very awesome. Well, it'll be really exciting to see this develop over the next couple of years. Very
Yeah.
cool.
Thank you.
You have a very exciting postdoc. All righty. That will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.